To run a CO2 reduction experiment, you might think we just drop two wires into a beaker. But if we do that, the oxygen produced on one side will float over and ruin our sensitive carbon reaction. To solve this, we use the industry standard, the H-cell. Imagine two separate chambers connected by a bridge. This shape physically isolates our carbon fuel from the waste oxygen, while still allowing electricity to flow. Inside the H-cell, we use a 3-electrode system. First is the working electrode, or the cathode. This is the centerpiece of the experiment, connected to the negative terminal. This is usually a copper catalyst where the CO2 is actually reduced. Second is the counter electrode, or the anode, connected to the positive terminal. This is usually a stable platinum wire that completes the electrical circuit by splitting water into oxygen. Finally, we have the reference electrode, typically made of silver chloride. This acts as a highly sensitive voltage sensor. It measures the exact energy at the working electrode without passing any current itself. To fill the cell, we use an electrolyte solution, usually 0.1 molar potassium bicarbonate. This conducts electricity and acts as a pH buffer. But the most critical part of the H-cell is hidden inside the bridge, the Nepean membrane. The membrane is the traffic controller. It acts like a microscopic filter that allows positive ions to cross the bridge and complete the circuit, but acts as a solid wall against gases. This ensures the waste oxygen never reaches our precious fuel. Now, we have to wire our cell to the computer power supply, known as the Potentiostat. Cable colors vary by brand, but the logic is universal. The red cable goes to the working electrode, the black cable goes to the counter electrode, and the blue cable goes to the reference. A critical warning here: if you accidentally swap the counter and reference cables, you will force high current through your delicate reference sensor and instantly destroy it. Before you turn on the voltage, you must create the right environment. The liquid is full of ambient air. If you start the reaction now, the electricity will be wasted. You must insert your gas tube deep into the liquid, known as sparging, and bubble pure CO2 gas vigorously for 30 minutes. Do not let the gas just sit above the liquid. It must bubble through to completely saturate the electrolyte. Once the liquid is purged, and you've checked for leaks, you are finally ready to flip the switch.